Okay, previously we had seen how we can apply the direct stiffness method onto a problem, right? So we had solved this problem. Okay, now the thing is that we actually had applied the boundary conditions later on after providing the entire matrix for this particular frame, this two-member frame. And the reason for that was that we actually wanted to get the reaction forces. I mean, once you get all of the deflections, what you can do is you can easily get the reaction forces from here. And once you get the reaction forces from here, you can easily calculate the shear force and the bending moment, right? You can even do the shear force and bending moment diagrams as well. Okay, but what if we just wanted to find out the deflections, right? What if we just wanted to find out the deflection? In that case, what we can do is we can apply the boundary conditions early on. I mean, looking at it, we know that there is going to be no deflection horizontally or vertically at point A, right? That is why u1 is equal to 0 and u2 is also equals to 0. So instead of forming the matrix and then cutting out this parts, what we can do is we can cut out the parts beforehand to make the matrix smaller for us to work with and get the deflections that are available there, right? Well, the drawback to that is that since we will not get the whole matrix idea, we'll not be able to determine the reaction forces from there. But what we can do is we can easily and more without spending more time, we can get the deflection. So if we had to just calculate the deflections, we can apply the boundary conditions early on, and that is what we're going to see. But there's also another thing that we're going to see. We're going to neglect the axial deformations as well, because from the values, if you look at there, the axial deformations are very less and they can be neglected. Okay, so neglecting them is not a very good idea. So whenever you are conducting the finite element analysis or the direct stiffness method via the help of a software or by computer programming, then you can do the whole thing. But when you're doing something by hand, it is going to take a lot of time that we have covered in the truss part, right? We have understood that in the truss part. So what we're going to do here is that we're just going to neglect the axial deformations and see how many deformations there are left and how easily we can calculate them without the help of any software or without the help of any programming language. That is what we're going to see here. Okay, so here is the problem that we're solving. So let me just quickly draw it up here. There you go. Let me just draw another version of it. There you go, the fixed support. Here is the hinge or the pin support. Sorry about my drawing. Okay, alright, so we have that here. We have A point, we have B point, and then we have C point. So I'm just going to draw up the available deflections here, not the forces or anything else like that. Okay, at first we're gonna have a rotational deformation here, which is theta A, right? Because the horizontal and the vertical will be cancelled out by the support. And here we're gonna have all three kinds. So we're gonna have theta B. Here we're gonna have UB, and on the vertical direction you can call that VB. We're going to have all that. And since this is a fixed support, there are going to be no deflections at all. Now, so we said that we are also going to cancel out the axial deformations, meaning we're going to consider the axial deformations to be very negligible, and we're going to consider them as 0. So can you tell me which are the axial deformations here? So think about it for a second in your head, and I'm going to reveal the answer now. So there are two members here. You can see the member AB. There you go, member A, B, and there's another member BC. So you can see the deflection UB, this UB right here, is actually causing axial deformation to member AB. So we're going to consider UB to be 0 because we're considering axial deformation to be 0 or to be very negligible. And now if we consider member BC, you can see that this force VB right over here, there you go, not force, the deflection, VB, there you go, is causing axial deformation to member BC. So we're also going to consider VB to be 0. So if you consider all of those things, you're going to see that we just end up with two unknowns. There you go. Since UB is 0, I'm removing that. Since VB is 0, I'm removing that. So in this entire frame, we are ending up with only two unknowns. The two unknowns being theta A and theta B. So these are the unknowns for us. So we're going to write out the matrix for AB member and the matrix for BC member, and then we're going to combine them. So let's just do that. If we write up the matrix for the KAB, let's write it here. KAB. There you go. It's going to be a 2 by 2 matrix because there are only two unknowns. So if you consider the member AB, so A is the first point of the member, so theta A is the third part, right? 1, 2, 3. So that is the third reaction. So if we go to our global matrix, there we go. So 1, 2, 3, meaning this column right here. There you go. That's 3. This is the column that we're going to be needing. So that's 1, 2, 3. And for B point, that is 1, 2, 3, 4, 5, 6. So 6 is this one. There you go. Similarly, we're going to need the third row and the sixth row. There we go. Now we're taking these because since it is member AB, the first three, there you go, the first three columns are for A, is UA, VA, then theta A. We only have theta A, that's why we're taking theta A. This rest of the three columns are actually for UB, VB, and theta B. So we only have theta A and theta B, that is why we're taking those columns. Similarly, the rows are divided in a similar manner as well. Okay, so from here we can guess which of the values we're going to be taking in the stiffness matrix. Okay, let me take the pen, different color. Okay, so 3, 3 is crossing off S3. So that is why we put S3 here. Let's call this notion theta A. Let's call this column theta B. Let's call this row theta A row. Let's call this row theta B row. Okay, so theta A, meaning column 3 by 3. We have, there you go, 3 and 3 is intersecting on S3. That is why we have placed S3 here. So when we're taking theta B and theta A, theta B is column 6. There you go, column 6. And then theta A is row 3. So column 6, row 3. There you go. Column 6, row 3 is S4. So we're going to place S4 here. Similarly, column 3, row 6 is, there you go, column 3, row 6 is S4. So S4. Right after that, column 6, row 6 is S3. So we have S3. So we have figured out KAB. Now we're going to figure out KBC. Okay, so let's just go to the next page. I think if I do it here, it'll be more easier for you to understand. Let me just remove all of these for now. Okay, now we're gonna do KBC. So remember here, since we're doing KBC, there's theta A, theta B, theta A, theta B. Now since we're doing BC, B is the first point in the member. So this displacement becomes the number 3 displacement. Because in this case, for member BC, this equations from here to here are the B variables, UB, VB, theta b, and these three are the c variable, uc, vc, and theta c. But we already know that these are 0 because there is a fixed support there. Let me just remove this axis writings. Okay. Let me remove this as well. Okay. So there is no A point, so there is going to be no theta A here. If we write out again, K, B, C equals to, you can see at BC member there's only one unknown, only one deflection, that is theta B. So there is going to be theta B by theta B. So that's going to be a 1 by 1 matrix. There we go. Theta B, theta B. And since B is the first member, so this is UB, this is VB, and this one is theta B. Similarly, okay, here it becomes UB, VB, and theta B. So this row is theta B row. So you get theta B row, theta B row. If we intersect it, we're getting S3. So we're going to write up S3 here, but this time we're going to denote it as S3 prime. We're denoting it as S3 prime because S3 is a stiffness matrix. This time the stiffness matrix is for the member BC. Luckily, the member AB and BC have the same properties, but what if member AB and BC were not same in length, or they did not have the same property, as I have mentioned in the previous lecture? In that case, S3 for member AB and S3 for member BC will have different values. So that is why we're marking the S3 for member BC as S3 prime, not just S3. Even though in this case S3 prime and S3's values are the same, but in some other cases it may not be the same. That is why we're marking it as S3 prime. So now that we have this matrix and as well as this one, so let me just write that up here. K BC is equals to S3 prime, the location is theta B by theta B. Now we can just write up the entire matrix. Okay, so if you write up the entire matrix, there you go. Okay, this one is for theta A, this one is for theta B, this one is for theta A, this one is for theta B. So we have A by A, so we have A by A is S3, so we write out S3. Then theta B by theta A is S4, S4. Right after that we have theta A by theta B, theta A by theta B is S4. Okay, and theta B by theta B, theta B by theta B here is S3, and theta B by theta B here is S3 prime, so S3 plus S3 prime. So this right here is the stiffness matrix that we are getting after neglecting the axial deformation and applying the boundary conditions early on. Okay, so we're done with this. Now if we move on, okay, let's move on, and here let me just erase all of these. Okay, now we're going to write up the Q and the F. So for Q force vector, we're gonna get 0 and 0 for both theta A and theta B. Because of the joints, you can see at the joints there are no moments, and rotational displacements are associated with moments, so there are no joint moments, so there are no joint moments here. Right after that we have fixed end moments. Okay, so the fixed end moment values will exist here. So for theta A and theta B, so for theta A, if we go back to the previous calculations here, at A, you can see there is a moment value, fixed end moment value, which is 12.5. So we're gonna write out 12 0.5 here. And if we look at B point, you can see there are two moment values. One is negative 12.5, another is positive 8.33. So if you do negative 12.5 and positive 8.33, you're gonna get negative 4.17. So we're gonna write up negative 4.17. So now we have K, we have our U, we have our Q, we have our F. So we can now just write up the matrix. And from the previous calculations, we also have the S3 and S4 values. So we had figured out that the value of S3 was 20,000 cubic feet per radian, and S4 was 10,000 cubic feet per radian. Okay, so we move on to the next page. Here we're just going to write the formula, which is KU equals to Q minus F. Okay, so for K we have S3, S4, then we have S4, and since S3 and S3 prime are the same, we're just going to write up 2S3. There you go. For U, the unknowns, we have theta A, theta B. For Q, we have 0 by 0 minus. For F, we have 12.5 and minus 4.17. Okay, now if we put them into equation formats, we are gonna get S3 theta A plus, we're solving the matrix right now, solving the matrix equation right here, S4 theta B equals to minus 12.5. This minus is actually this minus right over here. Okay, so let's just call this our equation 1. Now we're gonna get S4 theta A plus 2S3 theta B is equals to 4.17. So this is our equation 2. Now if we solve for this equation 1 and equation 2, already know the values of S3 and S4. We have the values right over here. So the unknowns are theta A and theta B. So we have two equations and two unknowns. So we can easily solve them, and we're gonna get the values of theta A and theta B. That is theta A equals to minus 7.74 into 10 to the power minus 4 rad, and theta B is 2.98 into 10 to the power minus 4 rad. So we have solved the unknowns. So solving for the unknowns like this is not very hard. This is quite easy. You can do it within 5 minutes or so, right? Well, it took me a little bit of time because I had to write using my mouse, and then I had to explain things to you. But when you are doing this by yourself, you don't have to explain it to anyone, and you can write it down on a pen and a paper, which is going to be very easy for you, and you will be able to solve the problem for theta N and theta B, neglecting axial deformation and placing the boundary conditions ahead. So in that way you can solve very easily using hand, even without software and programs. Okay, so that is it for this video. Thank you very much for watching. I hope you got to learn something new.